So we have a data set called exercise hours that came with our text. And it was a sample of 50 college students with the number of hours on average they exercise each week. There were 20 males and 30 females. And on average, the males exercised about 12.4 hours per week, and the females exercised about 9.4 hours per week. And what I want to ask here is there a significant difference in the number of hours the males exercised and the females exercised? And to do that, we kind of need to consider more than just the mean. So we'll have to develop some sampling distributions for each of these. Now, before we do that, let's just think a bit about the population we're dealing with, the proportion, the parameter we're dealing with, the sample and the statistic. So what population might I be considering here? And since this sample came from college students, then I would say I'm looking at a population of college students. Now, I have lots of different parameters measured here. The variable, right, is the hours of exercise per week. And then based on that variable, we can calculate things like the mean and the standard deviation, the min, quartiles, median, and so on. What I want to look at is the average, the mean, and whether there's a difference or not. So for example, my parameter then, parameter, would be the difference in the averages. Difference in means. So what that means is we first find the means and then we take their difference. So let's say population mean would be mu. I'm going to take the mean of the males and subtract the mean of the females. Now, these numbers down here aren't mu. Mu would be the population, all college students. Here I have the sample. So let's keep that in mind. So I'm curious about this. I don't know what that is, but I do have a sample, and I know the sample. So my sample here, 50 college students. And the statistic then I'm going to calculate, sort of partially calculated for me, is the actual average of these 50 males minus the actual average of these 50 females. So that would be 12.4 minus 9.4. So there's a difference of 3 hours. So this says, on average, males exercise about 3 hours more than females. And the question I'm wondering here is 3 really a significant difference? Or if we did another sample, would it end up being -3, where females exercise more? Would it end up being 0, where they exercise about the same amount? So I'm wondering, is this a significant difference? Is this a significant? So I have a question here. To answer that question, I need to know what my population is, my parameter, my sample, and my statistic. So is this a significant difference? I'm going to answer that. Now, what if it wasn't a significant difference? Well, that means there's like no difference between males and females. If there's no difference, that means they exercise the same number of hours. And so I'm expecting that maybe the actual difference is 0, right? So 0 in this case would mean there's no difference in how much they exercise each week. So is 3 close enough to 0 to say, yeah, it could be there's no difference? Let's figure that out. Some other things to think about here. Let's see, the females, according to the box plot, have a wider spread. They also have an outlier, someone that exercised an unusually higher amount of hours per week than the rest of the group. Males here have a slightly narrower spread and more variation in the middle 50% here. If we look at box plots, or sorry, histograms here, we can see, again, there's more females. The distribution is kind of sort of similar here. We get a clump in the middle, we get a clump on the left, and then we have a little tail out to the right. So they're both skewed right. So most people don't exercise much or exercise a modest amount, 10 hours per week. And there's a few people exercise more than the rest. As far as variation, thinking about the histogram, standard deviation is a measure of variation of a data set. but you can't compare standard deviations if the means are different. So notice they have different means here. So the correct way to compare variation is to calculate the coefficient of variation, which means you take the standard deviation and divide by the mean. So that's the measure of average deviation from the mean divided by where the middle is. And if you do that, you'll find that the males have a coefficient of variation about 71% away from the middle on average, but females is about 79%. So according to the coefficient of variation, females have a little bit more spread in the data from the middle than the males have. Males have, again, a higher mean. They have a higher standard deviation, but since their mean is higher, their percent change from the mean isn't as great as the females. Median males have a higher median, higher third quartile, but the females have a higher max. So there's a lot of differences in terms of who exercises more. And so it's a difficult question to wrap our minds around. So next thing I want to do is I want to take the female data, which I have a copy of from the spreadsheet, and stick it into StatKey and make a sampling distribution to see what the confidence interval is for the average. Because I can't just say the average is 12.4 for males, because that's just this sample. There's going to be variation. Every sample is going to be a little bit different. So sampling distribution helps me figure out how the samples might vary if I did many, many different samples. So I asked StatKey to make, based on the female data, a sampling distribution. So StatKey says, okay, the average is about 9.4. You can see that in the middle, sort of, it's kind of small. Write that down. 9.4-ish is the middle. And what we expect to find is a 95% confidence interval that the actual average number of hours per week college females exercise is somewhere between 6.9 hours here and 12.1 hours here. So we can then, if we wanted to, calculate that margin of error. Not too worried about that at the moment. But I think the average number of hours college females exercise is somewhere between 7 and 12 hours per week. Look at the males down here, and again, the males looks blown up compared to the females because I was trying to line up. Notice the 8 for males and females line up, the 12 for males and females line up vertically. I wanted to see how these confidence intervals overlap each other, if at all. So for males, the confidence interval centers at 12.4, like the data, and the average number of hours I think males exercise per week, college males, is somewhere between 8.7 and 16.3. And if I consider the overlap here, how do these intervals overlap? Well, this about 9, 8.75 is about 9. So there's some overlap here. And then 12.1 tracks down over here. So the actual population mean for the average number of hours females exercise and males exercise, they could be the same. It could be it's 10 for males and 10 for females, right? That's in both intervals. It could be 11 for males and 11 for females. The actual population mean might be in that shared range between these two. So could it be that males and females exercise the same amount of hours, even though my samples show these males exercise more? The answer is yeah, they could exercise the same amount of hours. Now, again, what I have here is a sampling distribution for mu for the females, and here's my sampling distribution for the mean for the males. I actually created a new variable back here, which was the difference between the two of them. So now I've got this new variable, the difference between the two of those, and I have this new statistic down here, the difference in their means. Right, 12.4 minus 9.4 is 3. So the next question I want to address is this right here. Is the difference significant, or is it really likely, is it possibly 0? So to do that, we have to run a different kind of sampling distribution. Now, the two I have here kind of answer that question, because there is some overlap. It could be they exercise the same amount and there's no difference between them. So over to StatKey. What I want to do is look at a confidence interval for a difference in means. So usually we've been going here. So I went here and I did the male data, then I went back there and did the female data. And I just had those displayed a moment ago. They are let's see, I think this one's the males. Yeah, I'll do that again just for fun here. Generate thousands of samples based on the male data. So I just made 7,000 samples, each of 20, those 20 males I started with. And the confidence interval here is 0.875 to 16.2-ish, pretty much the same as I had before. Female data, I copied and pasted into here. So here are my females. And generate thousands of samples. 8,000, it's fine, two tail. And so here again, I can see that's about 7 there and about 12 there, like the pictures I had earlier. And so now I'm going to put the two data sets together and do the difference in means. So heading over to the difference in means page, the data happens to already be there, which is kind of nice. And then I just, since it's already there, I don't have to copy and paste it in from the spreadsheet. I just generate thousands of samples. So again, I had 20 males, 30 females. I'm looking at the difference of their average, which was 3. What happens as I make a new distribution for that? So I've got 5,000, let's go 6,000, and look for a 95% confidence interval. And so remember, the margin of error here is approximately twice the standard deviation from the 95% rule in statistics. So here I get a confidence interval for the difference in their means is somewhere between -1.5 and 7.6. And I have a similar version of that already in my notes, I think. Nope. Let's put it in. So often when I'm playing with StatKey, either I copy and paste or I just draw on a piece of paper a rough sketch of this interval. So my rough sketch to go with this. Seen this before, x-axis, oh, my best symmetric bell-shaped curve. In the middle is that 3, that's my estimate of that mu difference there. And then StatKey says a 95% confidence interval is from about -1.5-ish to +7.6-ish. And remember, I'm looking at the mean, the difference in the means, males minus females. So the actual difference could be negative, which means the females actually exercise more, could be positive, meaning the males exercise more, and 0 is in this interval, right? Right over here is 0. The difference could be 0, meaning there is no difference. That is a possibility here. So do I have enough information to say that males exercise more than females on average? The answer is no, I don't. They could exercise the same amount. It is possible that there's no difference, that the difference is 0. So it turns out these confidence intervals are pretty powerful because I can combine them in different ways. I can compare two confidence intervals. I can put the two means together and make a new confidence interval and ask questions like, is there a difference between males and females in this situation? And the data suggests that there might not be, that males and females and college males exercise about the same amount on average, right? There's certainly going to be difference between individuals and in samples, but on average, all college students, they probably exercise around the same amount, is what this tells me right here. All right, let's look at a different example. So earlier in class, I had talked about a study the book brought up called The Organic Effect, where a Swedish family who ate a conventional diet was tested for pesticides in their bodies by collecting urine. And then they were given organic food for a couple of weeks to see if there was any difference in the concentration and number of pesticides in their bodies. And so we looked at the 3 BPA. Was there a significant difference before and after? And we determined, yeah, 0 wasn't in the interval. There was definitely a difference. Okay. So the next thing I want to look at is they also tested for 240 different pesticide chemicals. And what they found was that there were, before they started using organic, they found traces of 111 of these different 240 pesticides And then after they were eating organic for a couple of weeks, they found evidence of only 24 of those. And so the question here is, was there a significant decrease in the proportion of pesticides present? So we're looking again at a difference in proportions. And here we want the proportion of measurements resulting in pesticide detection while eating non-organics, that was before, minus the proportion of measurements resulting in pesticide detection while eating the organics. So I'm going to call these P, let's go B for before eating organic, because that's kind of the focus here. And then while eating organic would be after. So I'm going to have a PB, and that's the population one. And again, in this case, that would be the proportion pesticides detected. Before eating organics. And we have an estimate of that. It's approximately our sample data, P hat before, and that is the 111 out of 240. And then we've got this P after, so that would be the proportion pesticides detected after eating organic food. And we have an estimate, so P is the population parameter. These are my parameters, and we're approximating that by the sample data, P hat after, and that one was 24 out of 240. And I'm making this new variable the difference in proportion, so we'll call that PD for difference, which is the proportion before minus the proportion after, so 111, and so our estimate of that, our estimate of that is P hat difference, which is going to be that 111 over 240 minus 24 over 240. And give us, as a decimal, that is about 0.3625. And what would that be as a fraction? 76.85 out of 240 is the difference. But often we end up with a decimal version, so we're going to go with that. All right, what's the population here? Well, population here, this was done on a Swedish family. That's the sample. So somehow that Swedish family was chosen randomly based on, I guess, eating habits. What would the population be? Well, the population could be, say, all Swedish families. The population could be all families everywhere. So we'd have to decide what that population is, and maybe reading the original study might help us determine that. But I'm going to say the population here is Swedish families. And then these are my parameters, and my statistics are these P hats, the 111 over 240, the 24 over 240. My sample is that particular Swedish family, right? So we always have population in mind, parameters from that population. We have a sample, and then we have that sample calculation. In this case, we have a couple calculations. We're narrowing down to one. So this sucker right here, the 0.3625, this is my sample proportion, my sample statistic. Now, to answer the question, is there a significant difference? Now, there definitely is a difference in this sample. Now, every sample is going to be different, though. There's always sampling variation. So that's where we have to run a sampling distribution to see, okay, based on this sample, let's generate a whole bunch of other samples and see how wide the spread might be of possible differences. So we need to get over to StatKey. And here, I want to calculate a confidence interval for difference in proportions. We're going to get to the right calculator. And then I have to edit to enter the data. Now, I don't believe this data is already here. Nope, don't see it. So we're going to edit the data, and then they want my count, my numerator for group 1. So that was the before, the 111 pesticides found out of 240 they tested for. And then after, so is my second one, that would be the 24 pesticides found out of the 240 they tested for. So you get the numbers in the right spot. Computer calculates each of those as a decimal, and then it puts them all together, and looks like I can't subtract. It should have been 87 out of 240, or 0.363. So let me just fix my notes there. I can subtract from his head today, so that's an 87 right there, and they rounded that to 3 decimal places, 0.363, and that's fine too. All right, so once the data is in there, we just start generating thousands of samples based on this sample right here. And that'll give us an idea about how spread out other possible samples like this one could be. And so we get quite a bit of variation here. Let's go 6,000. And then let's grab a 95% confidence interval here, which should give us a margin of error, distance from the center of the edge, or half the width of the interval of about twice the standard error. So if we doubled 0.038, we're going to get 0.076, and that would be our margin of error. And there's our 0.363 in the middle, which is generally going to be pretty close to the data statistic, the sample statistic. So this shows us here that what we should expect is that in the general Swedish population, what we would find is the difference in pesticides detected before and after is going to be somewhere between 28.7% and 43.3%. And the question is the difference found significant? Well, if it wasn't significant, that means there's no difference in the pesticides detected before and after. No difference would be 0. The difference is 0, right? No, 0 difference. Is 0 in this interval? The answer is no. If that's 0.25 there and that's 0.5 over here, 0 is way off my screen. It ain't even in the ballpark here. So is this a significant difference? Yes, this is. There is a difference in the pesticides detected before and after, right? So sometimes when we look at situations and we see the sample data shows a difference, that doesn't mean there's actually a difference in the population. So remember, with the males versus females, we found that 0 was in the interval for the differences, which means there's possibly no difference between males and females exercising. In this case, in the difference in the pesticides, we're finding 0 ain't even close to being in this interval. So it means that the difference in pesticides detected before and after is significant. Eating organic reduces the number of pesticides that end up in your body. Now, you might say, well, they detected those in the urine. That means you peed them out. A lot of these pesticides are fat soluble, so they got stored in your fat for your liver to have to deal with at some other point in time when you burn that fat. That can be a problem. A lot of chemicals that end up in our foods that we eat turn out to be what are called obesogens, which means they help the body contain more fat, making people more obese, leading to all kinds of health issues, not just from the chemicals, but from the extra fat in our bodies that causes some trouble. So is there a significant difference eating organic? The answer is yes. What can we do about it? Try and eat better, try to get rid of some pesticides. We're slowly working on that in the world today. We might get better at it. You might remember that Happy Planet data that came up in the book. There was a correlation between income levels in a country, average income level, and life expectancy, income levels, and happiness. And one confounding variable might be in there. Well, if the people have more money on average, they can probably afford to eat better, and that might relate to their higher life expectancy. Now, I'm just guessing at how those confounding variables might jump in there. It's a possibility. There are studies on that. So we're just scratching the surface on what kind of things we can figure out based on collecting data. So hope you found this interesting. Good luck with all your statistical thoughts and work. I'll see you in the near future. Bye-bye.